This is Edexcel Further Pure 1 Numerical Methods, Euler's method for first order differential equations. To be able to follow this, you will need some understanding of differential equations from Year 13 A-level maths. When modelling real-world problems using differential equations, you quite often end up with linear differential equations and exact solutions can be found. However, some where exact solutions cannot be found and methods that find approximate solutions to problems are used, and these are numerical solutions. Here's an example. If we look at this curve here, dy by dx equals x plus the square root of y, that's non-linear because we've got y to the power of a half. And so we don't know any methods, and you won't be introduced to any methods that will allow you to solve that analytically during your A-level maths or A-level further maths. So with this non-linear differential equation not being soluble, we need to approximate the curve, and one way to do this is to use a series of straight lines, and the series of straight lines method is known as Euler's method. We'll take a look at how we can apply Euler's method to our example curve dy by dx equals x plus the square root of y, given the boundary conditions y equals 1 when x equals 1. And here I've plotted the point x equals 1, y equals 1. We'll also refer to that as our starting conditions. That's x naught, y naught. Now we're looking to move along a straight line a certain distance, and we'll refer to that next point that we're estimating along the curve as x1, y1. What we typically end up doing is choosing a regular interval for increasing x. And in this case, I'll just increase x by 0.1. So that'll give me x1 as being 1 plus 0.1, 1.1. Now our estimate for y1, we need to work out, we're going to use the gradient at 1, 1, and then know that x is increasing by 0.1. So let's work out the gradient at 1, 1. dy by dx equals, well, x is 1, and we've got the square root of 1 as well here. So dy by dx equals 2. Now I'm using that gradient. So for every 1 I increase x by, I'm going to increase y by 2. So if I've gone from x0 to x1 and I've increased by 0.1, I need to double that. That will give me y1 equal to 1.2. Here's that calculation presented slightly more formally. So we've worked out the gradient at 1, 1. We know the gradient is the change in y divided by the change in x. So we know the change in x is 0.1. We know the change in y is our value y1, take away y0, which is 1. So there's the change in y, that's the change in x, and we know that equals 2. So we can multiply up by 0.1 and add 1 to both sides, and that gives you y1 equal to 1.2. We can now use the values at y1, x1 to generate estimates for y2, and we know that we'll make x2 0.1 bigger than x1. So looking at the gradient at 1.1, 1.2, using our formula, we've got our x value is now x1, 1.1, and our y value is y1, 1.2. Putting that into the calculator gives us the gradient. And then we know the gradient is going to be the change in y over the change in x. So we're taking away y1 from y2, then rearranging and working the numbers out, we end up getting our estimate for y2 to be 1.4195. And you can see here from the diagram, it feels as though we've got a long way from our actual line with our estimates, but that's just there as a schematic to illustrate what is going on. Depends on the rate of change of gradient as to how far away we are going to be from the actual solution with regards to our estimate. Having gone through that example with numbers, we now need to formalize the work that we've been doing. So our starting point is going to be x0, y0. Our first estimated point is going to be x1, y1. The step increase in x is h, and the difference between y1 and y0 is y1 minus y0. So we can work out the gradient of the curve at x0, y0 because the given curve relates the gradient to some function of those two values. Our estimate says that we're going to use that gradient as a way of extrapolating up to y1. So we have our y1 minus y0 divided by the change in x. So it's a change in y divided by the change in x, and it's approximately equal to, because we're using a straight line graph. Rearranging that will give us y1 is approximately equal to y0 plus the change in x multiplied by the gradient at x0, y0. If we do the same again for x2, y2, we end up generating a very similar looking equation relating the gradient at our first estimated point, x1, y1, to lead us to y2 based on the change in y over the change in x. And rearranging again, we can see that y2 is approximately equal to y1 plus the increase in x, our h interval, multiplied by our gradient function using our x1, y1 values in that gradient function. So more generally, the next value of y is equal to the previous value of y plus the change in x multiplied by the gradient calculated from the previous point, xr, yr. Now we saw before that the estimate for the curve using a series of straight lines gradually gets further and further away when you get more and more steps. You can actually increase the level of accuracy of the approximation by reducing the step length. But of course that means you've got to do a lot more calculations. And so numerical solutions generally tend to lend themselves to computing intensive activities. So in this case, we could do it on a spreadsheet. And here is a spreadsheet for the function that we were looking at before. And I've gone as far as x being equal to 1.5 to generate an estimate for y at that particular point using steps of 0.1 in x. Laying it out in this fashion, even if you're not using a spreadsheet, when you're having to answer an exam question, will aid you in terms of making sure that you don't lose track of where you're going. But also to illustrate the point in terms of compute intensity, I've halved the step length here, and so taken 10 steps to get to my 1.5 estimate, and you can see that it is different. With further analysis and decreasing step lengths, you can end up determining how accurate your answer is. That was Edexcel Further Pure 1 Numerical Methods, Euler's method for first order differential equations. Next up, midpoint method for first order differential equations.